So the last talk will be given by Mária Paprskárová, correct? And it's about fragmentation of meteoroids.
Okay. Hello, everyone. My name is Mária Paprskárová. I'm a doctoral student at Comenius University in Slovakia. So, just like Tomáš, my supervisor is Juraj Todt. And today I would like to tell you about our work regarding fragmentation of meteoroids. So, first, some motivation why we do what we do. Well, it's actually pretty simple. We want to infer the physical characteristics of meteoroids. Yes, I know, very original. And since the only source of information for that is the light that comes from meteor, we need to focus on analyzing light curves. And if we are lucky and have multi-station observation, we can also additionally use dynamics. So, regarding the light curves, we decided to focus on the processes of ablation and fragmentation, which are really dominant in affecting its shape. And they are also closely connected to the structure and material of meteoroids, so they should be helpful if you understood them correctly. And, well, our approach is to model the behavior of meteoroids, including the fragmentation, and hopefully from our simulation we can get a good fit to the observations and thus estimate the properties of the meteoroid. When we have this kind of model, we can also run the simulation forward, including the dark phase, and hopefully predict a strewn field. And that could be a good way to verify our model, because that could be compared to either real data when some meteorites were found, or at least a prediction of different authors. Okay, so regarding the ablation and fragmentation, real quick, we need to understand how they affect the light curve. Ablation is a continuous process of mass loss from the surface. So its effect on the light curve is, it affects its shape overall. If the ablation rate is high, then the meteors are bright and short-lived. And if it's low, then the meteors last longer and they are dimmer. On the other hand, fragmentation can be at most called quasi-continuous because it's just repeatedly detachment of some mass of the meteoroid. But most of the time, and especially what we are going to focus on, it's just sudden detachment of a bunch of material that increases the surface area interacting with the atmosphere and leading to these kind of flare-ups on the light curve as compared to a standard non-fragmenting body. So now that we know how to identify fragmentation and ablation, we can move on to how our model works. It's actually pretty simple. We have the well-known standard set of differential equations for deceleration, ablation, and light emission, which then are computed for each object that we simulate. We can either simulate the meteoroid as a single body or a fragmenting one. When we include fragmentation, we need to find and select the fragmentation point manually. And each fragment that is generated is then simulated as completely separate and independent object. And since we don't know much about the meteoroid beforehand or its fragments, we just treat each and every one as a homogeneous sphere. We include the influence of gravity, atmospheric model, and also wind. especially for the dark flight, because that's when the meteoroid is already decelerated enough and the wind speeds are comparable to have high enough influence. For this particular work, we chose to analyze 3 cases captured by AMOS camera system. We chose such cases that had more than 1 station capture them because we also wanted to use dynamics. Naturally, we wanted the light curves to show signs of fragmentation, and as we can see on, it's run away. As we can see on the pictures, there is quite evidently something there. And from our estimates, which we used the PE criterion for, this should be of asteroidal origin, so material could be strong enough to potentially survive right until the ground. And now on to some results of our simulations. So this is the first case. We can see the observed light curve and plotted our best single body fit and our best fragmenting body fit. We have numbered all the fragmentation points that we added. It's not too detailed because we wanted to focus on the main features of the light curve, and also we wanted to make sure that the fragmentation points were present on light curve from all the observed stations, so they were really there. And this is a simplified fragmentation history. Each fragmentation point has a parent body, how many fragments were detached, and in the circle there is mass in grams. Now, we did this for all 3 meteors. Some of them had more detailed fragmentation history, some less. But overall, both single body and fragmentation simulation were pretty good matches to the observation. And hopefully the fragmentation was a little bit of an improvement. Now on to the trajectory. Well, we did the dynamics fit for each and every fragment that was created, but here is just an example showing the results from single body. It's obvious from the fact that the meteor decelerates that the most of the distance is covered when it's still in its meteor phase. And then we have a follow-up dark phase, which lasts 4 minutes, and it is strongly influenced by the wind. As we can see, here is depicted the wind direction and speed, and it correlates pretty good with the way it turns to the side there. This was also done for each and every meteor, each and every fragment, and now on to the most interesting part for us, the prediction of the strewn field. So we decided to plot where the best single body fit would fall. As we can see, here it is. And then we decided to take the last observed position of it and simulate if it was a different mass, where it would fall. And this created a line like this, which we already saw a few days ago, is a good way to predict the strewn field. And we were pretty happy when the leading fragment from the fragmenting simulation fell in the near vicinity of it. But a pretty interesting results showed itself when we simulated the tiny fragments that were detached along the way, because there we used the exact position where the fragmentation happened. And as we can see, they are all over the place. Well, we also simulated them with different mass and different time of fragmentation, because as I showed before, the fragmentation history is not too detailed, so the fragmentation times and also the fragments that were produced could have been of very, very variable properties, but more or less they always fell. The one fragmentation point, whatever mass we used, always fell in that location. And very interesting thing is that it didn't depend on their mass or the point at which they fragmented. We can look at fragments number 2, 3, and 4. They are basically right next to each other on this light curve. They were the same mass at the starting point, and despite all that, they fell into completely different positions. And this was all determined by the fact that when they entered the dark phase, they were caught by a different kind of wind. So, as we can see, all of the fragments are in agreement with the general direction of the wind. They are to the southeast of the original line. And regardless of their mass, they are quite mixed in here. And interesting thing is, if we continued the meteorite line, we would actually need a fragment large as this to fall to the distance that these fragments ended up in, which might lead to the conclusion that some sort of mixing of meteorites, which is sometimes observed on the sites where meteors are found, could be a result of this kind of process. We did the same for the other meteor. There is nothing too shocking. We can see that once more, there are fragments of very, very, very tiny mass where they shouldn't be, just from the single body estimate. And finally, I would like to point out a particular case of a bolide that was large enough that it was really thought to have produced some meteorites. They were unfortunately never found, but we had estimate of strewn field to compare it to. And as we saw in the Riebeck case, it should be a reliable estimate. So we were pretty happy that our results seem to agree with this prediction quite closely. And once more, the tiniest fragments did whatever they wanted to do. And yes, that's probably all of it. So just to summarize, we were able to model the fragmentation and the behavior of meteoroid in the atmosphere. We were able to reach a pretty satisfying fit of light curves and dynamics. When we used fragmentations, we actually got better results for ablation coefficient, because without fragmentation, it usually is much higher in the simulations because it kind of hides the fragmentation in itself. And finally, we also simulated the strewn field, and it seems to show reasonable results compared to what other authors predicted. And in regard of those tiny, tiny fragments that behave kind of strangely, it could be the explanation for fragments mixing on the ground, and it could be something else that we can look into in the future. And that's all, so thank you for your attention.
Thank you very much, Mária. We have again plenty of time for questions. Yes.
Thank you for your talk. What luminous efficiency are you using in your modeling? Because it influences on the field of light curve you get.
Yes, well, we tested a lot of them because there are. Oh, yes. Yeah, sorry. Yeah, so we tested a lot of luminous efficiency models, and we landed on the adjusted model from an article by Verick in 2012 who adjusted or corrected the luminous efficiency by Hill and collective. It was an older model and it was focused on the emission of iron, but this new article corrected its values for the most typical materials, chondrites and so on.
Is there any dependence on fragment size in your luminous efficiency?
It isn't, because we needed the photometric mass at the beginning, so we wanted to have a luminous efficiency that didn't include this dependence.
Because it would influence your result and your fragmentation and the size of your fragments. So you need to take this into account.
Felix, you had a question?
Hi, great talk. In your light curve data, did it saturate from the brightness of the fireball? And if it did, can you comment on what effect that may have had on your results?
The last one, the one that was also predicted to be the source of meteorites, that one was saturated. It was, yes, this one. We can see that it was actually very, very strong in the middle somewhere. And we tried to correct it by a calibration of this light curve, because we know that it was what we measured was too low of an absolute magnitude. So we needed to increase the brightness. And for that, we used a comparison between how much our cameras had lower measurements than other outers, which was a previous work of one of our students who did this kind of calibration on stars and planets and so on. So we had pretty good idea that when it didn't measure what it was supposed to be, it needed to be corrected some way. So yeah, we needed to lower the magnitude, so increase the brightness, yes.
So maybe a last quick question. Felix, you had a question?
I don't know whether it's quick. But let's see, otherwise we pick it up offline. In your last slide, you showed the strewn fields.
Yes.
And your first fireball, your cases 2 and 4, they are very much lateral shifted, which make me think that these fragments, they enter the deeper part of the atmosphere in a totally different geographical location. And that make me think that you use there an other wind model. So is that the case? Do you use for every geographical position an other wind model, or?
No, the wind model is not as detailed as we would want. So the wind model was the same for all of these, because the position of the station that collects the wind data this is the closest one we get, and there is nothing more for hundreds of kilometers around, so just that one. But it's true that these fragments, they entered at least the dark phase at a different heights, so the wind simply caught them at some different value of this one. Because as we can see, it is actually kind of quickly changing along the altitude.
So that means your fragmentation happens at very low altitudes.
It happens. It doesn't happen at low altitudes, at least not all of it. This one, for example, yeah, that was actually pretty low. It was about 40 kilometers into the atmosphere above the ground, and these ones I'm not really sure, but they were higher. So yeah, probably somewhere around that 45, 50 kilometers above, and they just were continuing the flight, being decelerated and entered the dark flight each on their own.
Okay, I think we should probably end this session now. Well, okay.
I'd just like to add one comment. You probably need to take into account the initial interaction between fragments at the fragmentation moment, which provides you lateral velocity perpendicular to trajectory. And this velocity could add the spread of your strewn field. I guess that some fragments are affected by this effect.
Well, we didn't account for interaction of fragments in the light phase of the meteor, but later when I was modeling these areas where the fragments might have been, I added some spread of their masses, of the time when they were detached, and also the speeds. Yeah, that.
Okay, I think we should probably end now and continue this discussion during the coffee break. So thanks again to all the speakers.